Swayam Prabha. Digital India. Educated India.
Laplace transform makes the solution of linear ODE with constant coefficients quite simple. How, that we shall see with examples. So I will give you some differential equations. Say the given equation is like this. This is equal to input, and say the input is delta t, maybe with some coefficient 2. And initial conditions, suppose they are y at 0 minus equal to 1 and dy dt at 0 minus is equal to 2. This is a second order equation, so we need two initial conditions. Now let us see how to solve this. First thing we will do, we will take one-sided Laplace transform of both the sides in this equation. One-sided or unilateral Laplace transform. So that means we have to multiply both the sides with unit step signal like this. And this is equal to the right side multiplied with unit step. Whether you call it unit step or not, essentially you must remember that when you multiply this, you should not erase the value of these signals at time 0. Particularly for delta t, you should not erase delta t at time 0, then nothing will be left. So this we were denoting with a small minus sign below u. This is our special symbol. So standard symbol in textbook is just to write ut. Okay, now we will take Laplace transform of both the sides like this. Okay, so what will be the Laplace transform of this term? Suppose the Laplace transform of y u, that is unilateral Laplace transform of y, is capital Y of s. So this one-sided Laplace transform of the second derivative, we know it will be y s multiplied with s square minus s value of y signal at 0 minus y dot or dy dt at 0 minus. This one will be 5, then s into capital Y s and minus y small y at 0 minus. Okay, then this third term is 6 into capital Y s, and the right side is equal to 2 times Laplace transform of delta t is 1. Okay, then let me collect capital Y s together. So I have capital Y s multiplied with s square here, 5s here, and plus 6 plus, let me bring all other terms to the right side. Okay, so here I have 2, then from here 5y 0, so 5y 0 minus this term, then here plus s y0 minus this term, and plus y dot 0 minus. Now let me put the values of y0 minus. So I will have 5 plus s multiplied with y0 minus, which is 1, plus y dot 0 minus is 2. Then I will write capital Ys equal to 2 plus 2 4 plus 5 9 plus s divided by this term s square plus 5s plus 6. Now capital Ys is nothing but Laplace transform of yt ut, and therefore yt ut will be equal to Laplace inverse of this 9 plus s divided by s square plus 5s plus 6. Now we have to calculate Laplace inverse of this function. Remember that we told you about this formula for calculating Laplace inverse. However, in practice we do not use this formula. Laplace inverse is always calculated in practice by looking at a table of Laplace transform, where you have some standard functions like ut, delta t, sine omega naught t, etc., and you are given the corresponding Laplace transforms like 1 over s, 1, etc., etc. What we do, we have to remember these standard formulas, and then given any arbitrary function, we have to reduce it as a combination of these standard Laplace transform formulas. Okay, and from that we will calculate Laplace inverse by consulting this table. Now, to reduce this function as a combination of standard Laplace transforms, one trick we always use, that is called partial fraction. We will learn this with examples. Okay, so this is equal to Laplace inverse of 9 plus s divided by this denominator. I will factorize. In this case it can be written as s plus 2 multiplied with s plus 3. Next, this ratio of two polynomials can be written as something divided by s plus 2 plus something divided by s plus 3. Now a and b will have some values, so that this is equal to this, and we will determine the values of a and b such that these two terms are equal. Okay, so we want 9 plus s divided by s plus 2, s plus 3 should be equal to a by s plus 2 plus b by s plus 3 for some values of a and b. Now let me multiply both the sides with this denominator. So here I will have 9 plus s. The right side will become a multiplied with s plus 3 plus b multiplied with s plus 2. I am multiplying this denominator here. Now this should be true for all values of s. Okay, so this should be true for all s. This is an identity. Now if we put s equal to minus 3, then this term will be 0. So we will get here 9 plus minus 3 is 6. This term will be 0 plus b and s plus 2. That means minus 3 plus 2, that is minus 1. Okay, so from this we can write b is equal to minus 6. In the same way, if we put s equal to minus 2, then 9 minus 2 is 7. Here a multiplied with 3 minus 2 is 1 plus this will be 0. From this we can write a equal to 7. Okay, so from this let us go back here and let us put the values of a and b. So we will have 7 by s plus 2 and b is minus 6 by s plus 3. Okay, so this is YTUT. Fine. Now this can be written as Laplace inverse of 7 by s plus 2 plus Laplace inverse of 6 by s plus 3. Now you remember your standard Laplace transform table, and then you will recognize that Laplace inverse of this is equal to 7, this constant, multiplied with e to the power minus 2t ut. In the same way, Laplace inverse of this term is 6 e to the power minus 3 t ut. Here this is minus, so this is minus and this is also minus. Okay, that's the answer. Next we are going to take another example. Again we have a second order differential equation. Input is unit step function now, and initial conditions are y0 equal to 2 and y dot 0 minus equal to 1. Okay, now we have to solve this for time greater than equal to 0. Again we will take one-sided Laplace transform. So Laplace transform of d2y dt2 multiplied with ut or u minus t plus 2 into Laplace transform of dy dt ut plus 2 into Laplace transform of yt ut, and then the right side Laplace transform of ut multiplied with ut is ut itself, and Laplace transform of ut is 1 over s. Let me write it directly. Okay, now this is equal to capital Y s multiplied with s square minus s y 0 minus y dot 0 minus. Okay, so this is the first Laplace transform, where capital Y is the Laplace transform of yt ut as before. Okay, then plus the second term 2, and this will be s capital Y s and minus y 0 minus, then plus this is 2 capital Y s, right side is 1 over s. Okay, now let me collect capital Y together. So capital Y is multiplied with s square plus 2s plus 2. Okay, then I will write all other terms in the right side. So this is equal to 1 by s, then plus s y 0 minus, then minus that will be plus y dot 0 minus, then plus 2 y 0 minus, this one. Okay, now this is equal to 1 over s plus, let me put the values. Y 0 minus is 2, so this is 2s, and here 2 into 2 is 4, so 2s plus 4. Okay, and y dot 0 minus, this one is 1 plus 1, so that is equal to 2s square, then plus 4 plus 1 5 is plus 1 divided by s. Okay, now let me divide this. So we have capital Y is equal to 2s square plus 5s plus 1 divided by s into s square plus 2s plus 2. This can be simplified a bit. Let me write, by taking 2 common, we have s square, then here we have 2.5s, I will write 2s plus half s, and here we have half, I will write 2 minus 1.5 divided by s of s square plus 2s plus 2. I have done this intentionally so that now I can write this as 2 terms. One is this part divided by this, another this part divided by this. So the first term will be 2 multiplied with this divided by this, that will become 2 by s, because this part and this part will cancel in the first term. Okay. Plus here we have s minus 3 divided by s of s square plus 2s plus 2. Next, I will try to get a partial fraction for this second term. So I will write this as 2 by s plus something a divided by s and plus something divided by this other factor s square plus 2s plus 2. Now since this denominator here is quadratic, I will take the numerator to be of first order b plus cs. So this will be true for some values of a, b and c. Okay, now that means we need s minus 3 divided by s then s square plus 2s plus 2 to be equal to a divided by s plus b plus cs divided by s square plus 2s plus 2. Now I can cross multiply this denominator, so I will get s minus 3 equal to a multiplied with this s square plus 2s plus 2 and plus this b plus cs multiplied with s. Now this is true for all values of s. This is an identity. So if I put s equal to 0 to make this term disappear, then here I have 0 minus 3 is minus 3 equal to a, this is 0 0 2 and this is 0. That implies a is equal to minus 3 by 2. Now we may put other values of s in this identity and thereby we will get b and c. Okay, so let me try with say s equal to minus 1. Then this will be minus 4. Here a is already known, this is minus 3 by 2. S square will be 1, then this is minus 2 plus 2, that will cancel, plus here b minus c and minus. Okay, so this is one equation. Similarly, if we put some other value, say is equal to 1, we will get 1 minus 3 is minus 2 equal to a is 3 by 2, minus 3 by 2, and here 1 plus 2 plus 2, so 5 plus b plus c multiplied with 1. Okay, so this is one equation, this is another equation. This is equal to minus 4 and this is equal to minus 2. Okay, now if we add these two equations, call it 1 and 2, then b will cancel. Okay, so from 1 plus 2, here we have minus 3 by 2, minus 3 by 2, minus 3 by 2 common, 1 plus 5 is 6, then minus b plus b cancels, then plus c, 2c equal to minus 4 minus 2 minus 6. Okay, so from this 2c equal to minus 6 and plus 339. So that means c will be 3 by 2. Okay, 3 by 2, and then we can calculate b. Okay, so from equation 1 we have minus 3 by 2 here, then minus b, then plus c, which is plus 3 by 2, is equal to minus 4. So minus plus cancels. This implies b equal to 4 if my calculations are correct. Okay, so we have got b equal to 4, c equal to 3 by 2, and a minus 3 by 2. So let me put these values here. Okay, so then we will get ytut is equal to Laplace inverse of 2 by s. Then let me copy this. Okay, and now the value of a is minus 3 by 2, b is 4, and c is plus 3 by 2. Okay, so this is equal to Laplace inverse of 2 minus 3 by 2, that is half s, then plus 4 divided by this thing, and this denominator can be written as s plus 1 whole square plus 1 square. You can check. I have done this by inspection. S plus 1 whole square plus 1 square. Then this term plus 3 by 2 s divided by s square plus, so this also I will write in this way, s plus 1 whole square plus 1. Now we have to recognize that which are the signals for which these are the Laplace transforms. So this one you can easily recognize, it is half 1 over s is Laplace transform of ut. Then these two terms you look at, it looks like a square plus omega square in the denominator. So these two terms are going to give us some sine and cosine signals. This will give a sine signal, this will give a cosine signal because we have s in the numerator. But also since here instead of s square we have s plus 1, so what we will also have some e to the power minus 1t will also be there. Okay, so I will do this. I will put a plus 1 here and I will adjust here minus 3 by 2. Okay, now I can put a bracket here. Now this is 4 minus 3 by 2, that is 5 by 2, and then the Laplace inverse of this will be sine omega naught is 1, so 1 t multiplied with e to the power minus this one t whole multiplied with ut. Okay, that is this term plus from here 3 by 2. This is the Laplace transform of cosine omega naught is 1 t e to the power minus 1 t whole multiplied with ut, and that is the answer. Now you may rewrite this nicely by taking similar terms common in this way. That is the final answer. Okay, let me now take some practical, although simple examples. Here we have a simple circuit. One coil with inductance L and resistance R is connected in series with a battery of EMF E and internal resistance small r. This switch is closed, so current will flow in this circuit like this, and this switch is open, so no current can flow through this, and this current you can calculate as I equal to this battery EMF divided by total resistance capital R plus small r. Okay, and this circuit is in steady state in the sense that the switch is closed for a sufficiently long time, and the current is therefore now has reached a constant value. And you know that when we apply a DC voltage across an impure inductor, then the pure inductor acts like a short circuit. So this is the steady state current. Now at this state, suddenly somebody closes this switch, suppose at time t equal to 0. Then this circuit completely changes at time t equal to 0. Now there is a path for this battery to drive current, and the battery will like to drive current through this short circuit or least resistance path instead of through this R and L. However, there was this current E by R plus small r previously through this inductor. So now will this current stop immediately, or what will happen? Let us see that. Okay, for that let me call the voltage across this inductor as VL. Okay, and let me take this upper side as positive, lower side as negative. This is my chosen reference direction, and then the current is chosen in this direction, that is from top to bottom. So according to the physics of circuits, physics of inductor, this voltage is given as L inductance multiplied by di dt, and this voltage across the resistance, let me call that VR, according to Ohm's law, this is equal to IR. The reference direction is plus upside and minus downside. Okay, then the moment you connect this switch, I can consider a closed path, closed circuit like this, and in this closed circuit, Kirchhoff's voltage law tells me that the total voltage drop in this closed loop should be 0. So I can write this voltage VR plus this voltage VL plus 0. There is no voltage drop. The switch has 0 resistance. So this should be equal to 0 according to the Kirchhoff's voltage law. Okay, but this is true only after time greater than equal to 0. This is not true before time 0, because then the circuit was completely different. Now we want to determine this current I as a function of time for t greater than equal to 0. We want to know how this current changes through the inductor after you close this switch. Okay, so let us first write some differential equations from from our knowledge about this circuit, and then we will solve that differential equation. Let me start from this KVL and let me write VR is equal to I multiplied with R, VL is L di dt, and this is equal to 0. So if you think this I as the output of a system, then this is a differential equation with right side being 0, so we have no input. However, we have some initial conditions. The initial value of I at 0 minus is equal to this. Okay, let me call it I0. Okay, some constant value. So this initial condition is given. This differential equation is derived from the KVL applied to this circuit, and we have to find I for all time greater than equal to 0. Okay. Okay. Suppose we consider IT ut, and the Laplace transform of that is equal to, say, capital IS. This function inside these braces represent the current starting at time 0 and afterwards. Okay, so this product has no information about the current before time 0. Okay, if so, from this equation, call it equation 1, from equation 1, taking the Laplace transform of both the sides, one-sided Laplace transform of course, we can write Laplace transform of this R is a constant, then it, and since we are taking one-sided Laplace transform, so let me multiply this step signal plus L constant, then Laplace transform of di dt multiplied with ut, that is unilateral or one-sided Laplace transform, and right side, even if you multiply with ut and take Laplace transform, you are going to get 0. Okay, and we have assumed that this Laplace transform is is. Therefore this will become r multiplied with is plus this is L constant multiplied with this will be is multiplied with s minus I0 minus right side is 0. Okay, then let me write is common multiplied with r plus ls then minus I0 minus, let me bring it to the right side, I0 minus. From this is will be equal to I0 minus divided by r plus ls. Now is is nothing but one-sided Laplace transform of this it. So from this we can write ITUT is Laplace inverse of this thing Li0 minus r plus ls. Let me now bring these constants outside. So L constant, I0 minus constant divided by, from here another L I will take, and then Laplace inverse of 1 divided by here S plus R by L. Okay, so here we have I0 minus, L cancels, and Laplace inverse of this thing you can readily recognize. This is e to the power minus this term r by lt multiplied with ut, and you can now put the value of I0 minus, which is given in our initial condition, that is I0, capital I0, which is capital E by capital R plus small r. Okay, so you can put that value E by R plus small r, e to the power minus R t by L ut, and that is the answer. Now you may plot this current waveform. So that will be this constant and then exponentially decaying pattern, something like this. This initial value will be this E divided by capital R plus small r, and then it decays. This is only the right side of this current waveform, ITUT. The left side, we cannot say that from this calculation. We know that from our circuit knowledge that this circuit was in steady state and some constant current was flowing. That we know, but from the solution of this differential equation, we cannot say anything about the left side part. We only can say about the portion starting from time 0 and afterwards. Now I just want to make some comments about this kind of circuit problems. Is that after writing this differential equation, we are taking one-sided Laplace transform. Okay, it is always the case that for similar problems we take one-sided or unilateral Laplace transform, that is by multiplying these signals with ut. We do not consider full bilateral or two-sided Laplace transform. We don't do that. Now whether we can do that and solve it, that is a different question, but also two-sided Laplace transform in this problem does not make any sense, because this differential equation that we have written is true only for time greater than equal to 0. Before this system was not like this. This system is created at time 0 by closing this switch. Before this system was not there, or some other system was there. Okay, so physically taking both, two-sided or bilateral Laplace transform on this differential equation is meaningless. Here is another example. We have a resistance and a capacitor connected in series with an AC voltage source whose voltage is given by Vt equal to A sine omega t, suppose, with this side positive and this side negative reference. Now say somebody closes this switch at time t equal to 0. That means before that this switch was open and no current could flow through this R and C. Now the moment you close this switch, current will start to flow through this R and C, and this is an AC source, so current will flow through this RC series combination and it will oscillate with time, and we want to know how that current or the voltage across the capacitor changes with time after the switch is closed. Okay, that is our problem. So we have to determine the current, this current here, and the voltage across the capacitor as a function of time after t greater than equal to 0. Let me call the voltage across this capacitor as Vc t, with the upper side as positive and lower side as my negative reference. The voltage across this resistance is Vr, function of t, with the upper side as positive reference and lower side negative. This current is a function of time it. So we have to determine how it changes and Vct changes after the switch is closed. Okay, now after this switch is closed, you can consider this closed loop and write a KCL equation, KVL equation, Kirchhoff's voltage law. Okay, so we can write this voltage Vt, that will be equal to the voltage drop across resistance Vrt plus voltage drop across capacitor Vct. This is for all time t greater than equal to 0. Note that this equation is not true before time 0 because the switch was open and the circuit was completely different, or the system was completely different. Now Vr is equal to R resistance times It according to the Ohm's law. considering this plus minus direction and the chosen direction for current. In the same way, we have seen earlier that this voltage and this current, capacitor voltage and this current are related in this way. IT in this direction from top to bottom is equal to capacitance C multiplied with the rate of change of this voltage VCT with the upper side taken as positive. Okay, this is Ohm's law and this is from the principle of capacitor. Okay, then here I can write VR equal to this R, and in place of I will put this RC dVC dt. You can solve this problem in different ways, no problem. I am just doing in one way. Now I will write a differential equation from this KVL. So starting from here, I can write VR, let me repeat, VRT plus VCT is equal to this VT, and in place of VR let me put this RC dVC dt plus VC. This is equal to VT. In place of VT let me just put A sin omega t. So this is a differential equation where you can consider this capacitor voltage as the output, this voltage as the input, and we need some initial condition, and suppose the given initial condition is that the capacitor voltage before closing this switch was V0, some constant value given, due to the stored charge in the capacitor. Before this switch was closed, no current was flowing, but the capacitor can have some stored charge due to what might have happened in a long history earlier. Okay, it can have some stored charge which will not get discharged when the switch was open, and due to that the voltage was V0. So we can say that the capacitor voltage VC at time 0 minus just before the switch was closed is equal to V0, which is given. So we also have an initial condition and a differential equation with the input given. So we have to solve this and get capacitor voltage as a function of time for all time greater than equal to 0. Let us do that. Okay, so from here, let me call it star. So from star, let me take the one-sided Laplace transform of this equation. So I will have Laplace transform of this thing, RC common I will write outside, then the signal dVC dt multiplied with unit step signal, because we are taking unilateral Laplace transform, plus here unilateral Laplace transform of this, that is Vc multiplied with ut, and also right side Laplace transform of A sin omega t multiplied with ut. Okay, now if the Laplace transform of VCUT is capital VCS, then here we have RC, and this Laplace transform will become S into VCS minus VC at 0 minus. Okay, and the right side, A constant, Laplace transform of sine omega t ut is omega divided by s square plus omega square. Now I will take VC common and write V capital VCS multiplied with RCS here, and then plus 1 minus RC small vc 0 minus. This is equal to A omega by s square plus omega square. I can bring this term to the right side like this and plus here. Okay, then from this, capital VCS is equal to A omega divided by s square plus omega square, this whole divided by RCS plus 1, and then here RC VC 0 minus whole divided by RCS plus 1, right? Now to get Laplace inverse of this, that is VCT ut, we have to take Laplace inverse of the right side. Laplace inverse of A omega divided by s square plus omega square, here RCS plus 1, and then Laplace inverse of this thing. Okay, here I will divide the numerator and denominator with RC, so I will have VC 0 minus divided by S plus 1 by RC. All these manipulations I am doing because I want to bring this as in the form of a combination of standard Laplace transforms. So this part is already similar to a standard Laplace transform you may recognize. For this part, I have to apply partial fraction here. Now this term, A omega divided by s square plus omega square and RCS plus 1, you can do a partial fraction in this way. Say s square plus omega square under p plus qs for some value of p and q plus m over RCS plus 1 for some value of m. That is one way. Another way is like this. Notice that s square plus omega square, this can be written as s plus j omega s minus j omega. Therefore, I will write this as something p divided by s plus j omega plus q divided by s minus j omega, and say something m divided by rcs plus 1. This is another way. Now we have to find the values of p, q and m. Okay, for that let me cross multiply this denominator. So I will get a omega equal to p multiplied with s minus j omega and rc is plus 1, then plus q multiplied with s plus j omega and rc is plus 1, and then m multiplied with s plus j omega is minus j omega. Okay, then this is an identity true for all values of s. So let me put s equal to j omega, then we will get a omega equal to this term will be 0, so 0 plus q into this will be 2j omega, then this will be 1 plus rc j omega, 1 plus j omega rc, plus this will be again 0 because this is 0. So from this you can get q equal to a omega divided by 2j omega, then 1 plus j omega or c. Now let us put s equal to minus j omega. Then this term and this term will be 0. We will get a omega equal to p, this will be minus 2 j omega, then here we will have 1 minus j omega rc plus this term will be 0, this will also be 0 because of this term. So we get p equal to a omega divided by minus 2j omega, then 1 minus j omega rc. Next, to get the value of m, let me take s equal to minus 1 by rc. Okay, so now let me put s equal to minus 1 by rc, so that here from here we will have a omega equal to this term will be 0 because s is minus 1 by rc, so this will be 0. Okay, and plus this will again be 0, and here we will have m multiplied with minus 1 by rc plus j omega and minus 1 by rc minus j omega. So from this m will be equal to a omega divided by the product of these two terms, okay, which will be 1 by rc square, 1 by r square c square minus j square omega square, minus j square omega square. So that is same as a omega divided by j square is minus 1, so we will have 1 plus omega square r square c square divided by r square c square, which I will write here r square c square. So we have got the value of m, p, q. So now let me come here. Let me call this equation star. Then from this equation, so this is equal to Laplace inverse of we have three terms for this: p by s plus j omega plus q by s minus j omega plus m by r c s plus 1 plus Laplace inverse of vc 0 minus divided by s plus 1 by r c. Okay, let me divide here by RC, so that will be M by RC and denominator will be S plus 1 by RC. So this is equal to Laplace inverse of P by S plus j omega, then Laplace inverse of Q by S minus j omega plus this term and this term I will write together as M by RC plus VC 0 minus and Laplace inverse of 1 over S plus 1 by RC. Now this is equal to, the first term is P e to the power minus j omega t, this thing, then ut. The second term is q e to the power minus plus j omega t ut, then plus m by rc plus vc 0 minus and e to the power minus 1 by rc t ut. You may take these ut's common and let me then put the values of p, q, m, etc. So the value of p is here. Okay, then this p multiplied with e to the power j omega t. The value of q is a omega divided by 2 j omega 1 plus j omega rc multiplied with e to the power j omega t. Okay, and let me take this ut common plus this term. Value of m is here. Okay, this is m, then divided by rc. So let me just erase these squares, plus vc 0 minus whole multiplied with e to the power minus t by rc, then ut. I have missed a minus sign here, this minus sign. Okay, then this omega can be cancelled, and now you have to simplify this somehow. This is what we have now. I will take this a by 2j common outside. like this. Then this is what we have now. Here this denominator and this denominator, they are complex numbers, and I will write them in terms of their magnitude and angle like this: root over 1 plus omega square r square c square with an angle theta, where theta is equal to the angle of this number, that is tan inverse the imaginary component omega r c divided by real component is 1. Okay, similarly here I will write this as root over 1 plus omega square r square c square, and the angle for this number will be minus theta because of this minus sign. Okay, you see this angle and its angle, they are negative of each other, so this is minus theta. Now this theta downstairs can be written as 1 angle minus theta upstairs, or you may write this as e to the power minus j theta. In the same way, this minus theta downstairs can be written as e to the power plus j theta upstairs. Okay, so now this is equal to a by 2j, and this denominator is common, 1 plus omega square r square c square, and then here this exponential together with this exponential can be written as e to the power minus j omega t minus theta, and this minus sign, then plus these two exponentials together is same as e to the power minus plus j omega t minus theta ut, and then this term I will keep as it is. Okay, then this is equal to a by root over 1 plus omega square r square c square. Okay, and then these two exponentials divided by 2j is same as sine omega t minus theta, then ut, and this term I will keep as it is. Now if you want, you can take this ut and this ut common like this, and that is the answer. Now this is our VC TUT capacitor voltage starting from time 0. Now you have a few homeworks. Firstly, draw this function as a function of time. Secondly, find the value of capacitor voltage at time 0 plus, and so that this is equal to the voltage at time 0 minus. This means that the voltage across the capacitor immediately after this switch is closed will be same as the voltage immediately before this switch was closed. That is because for this voltage to change, some charge need to come and get stored here in this capacitor. But for that we need some time, no matter however small that time is. Next, you also have to find this current as a function of time after time greater than equal to 0, and that is your third homework. Okay, that is this. Now let me finish this with an interesting observation. See, we started from the KVL equation in this loop. From that we wrote this differential equation, and then we took the one-sided Laplace transform of this differential equation, and we got this. Here the right side is Laplace transform of a sin omega t ut. However, notice that this generator voltage is a sin omega t alone. There is no ut here. We are getting this ut here because we are taking one-sided Laplace transform. And that is actually because this differential equation is true only after time greater than equal to 0. Because before that, the switch was open. We cannot write this KVL before the switch is closed. So the system was completely different before time 0, and that is why we are getting this ut. With that observation, let me stop today.